Okay, great. We can see it. Pablo Garcia has a degree in physics from the University of Oviedo, with a master's degree in nuclear engineering from CIEMAT and the University Autónoma of Madrid. After several years in the engineering of the Centralized Temporary Warehouse (ATC) project in Spain, he currently works as engineering and claims manager at Spanish nuclear risk insurers. Pablo began his collaboration with Jovenes Nucleares, managing disclosure talks in high schools, and then joined the board of Jovenes Nucleares in 2014 and is currently the chair of the commission. So he's currently the president, our president of Jovenes Nucleares. Thank you very much, Pablo, and I'm sure the presentation will go great. So I'll leave the floor to you.
Well, thank you, Alex, for your introduction, and well, good afternoon to everybody, and thank you very much for joining this third session of this course on nuclear fusion basics. First of all, I would like to mention that my approach to this lecture, to the latest on inertial confinement fusion, is going to be quite conceptual, and I am not going to explain any hard technical details, and I will try to fit in time as best as possible. So, however, I remind you that there will be a Q&A so we can solve your doubts then. So let's go. Okay, so as a brief reminder of the previous sessions of the course, I would like to highlight that the most important thing that anybody needs to know about nuclear fusion is that although it is a highly exothermic reaction, it is not spontaneous. And we need to provide activation energy to the system. We will favor the reaction by raising two parameters, temperature and pressure, up to an extremely high point where we will get a plasma. And as you have already been told, one of the ways to control and manipulate plasma is the inertial confinement or I.E. fusion, where we look for ignition to happen in an extremely short confinement time, maximizing both the temperature and the pressure of the system. I.E. is based on shooting these small plastic capsules filled with deuterium and tritium into a great vacuum chamber and heating them very much with really high power pulsed lasers. And just to end with a brief resume of the road so far, you already may know that we are still facing major challenges to reach a commercial operating fusion reactor, and that the schedule depends on fusion-related laboratories to solve all these challenges you can see in the slide. Common challenges, magnetic confinement challenges, I.E. challenges. So we've just reviewed the main facility that is trying to overcome magnetic confinement challenges, this ITER project. And now we are doing the same for the inertial confinement fusion. So where is nuclear fusion today? Well, you just saw ITER. And if we compare nuclear fusion with the development of nuclear fission reactors, if I have to be completely sincere, and I know this will disappoint many of you, we're still in generation 0 reactors, just like the first Chicago Pile 1 fission reactor, which was a pure research facility back in the 1940s. And the main one of those pure research facilities and truly big laboratories dedicated to I.E. fusion, to inertial confinement fusion research, is the National Ignition Facility, located in California in the United States, and it's currently the reference ICF facility. It's 192 laser beams, each with the capacity to deposit 2 megajoules of total energy, make NIF the laser with the highest energy in the world. NIF's reaction chamber allows laser configuration both for direct and indirect lining of the target with approximately 1% efficiency. In these images, you can see what NIF is like, okay? And it's just remarkable that the vacuum chamber here, where the magic comes to, it's only a small part of the facility, which mainly consists on allocate. You can see all these spaces to allocate all the laser beams related equipment. And as I told at the beginning of my lecture, I'm not going to explain any technical details, but about NIF. But I think it's important to remark that as the reference IC facility, NIF, the National Ignition Facility, lining is on an indirect target, as you can see in this figure, and that we're working with laser efficiencies up to 1%. So this means that if we want to deposit 2 megajoules of energy on the target, we need to generate a 200 megajoule laser in the very first moment, because part of that energy gets lost in each and every optical event on these components you can see in this laser system description figure. And that is the reason why what we say that laser efficiency is one of the major challenges on inertial confinement fusion. If we don't improve this topic, it will be absolutely impossible to get a profitable inertial fusion reactor. Well, here you can see a brief video that shows how NIF works and how the laser beams are generated and are amplified several times, okay? The beams are also collimated, which means something like cleaned, or in terms of light, that we try to, that every photon in the beam has the same energy. And then they are, as I mentioned, they are amplified several times. Then they are focused next to the vacuum chamber. They are up, they're rising, reaching the vacuum chamber. So here they are focused on the vacuum chamber, and they are shot to light the target. And as we just said, this lining is an indirect lining. Finally, as this is inertial confinement, we get the ignition in an extremely short confinement time. Here you can see 20 billions of seconds. This is the confinement time. So I know I have mentioned too many times the challenges of IC, and I don't want you to leave this course. So I have to remark that in 2013, NIF reached the so-called Breakeven Event, which means that we got, for the first time, more energy from the fusion reaction than what we put on the target. This does not include the energy we spent in generating the laser beams and gets lost due to the low laser efficiency, but it's still really good news. And well, we said that NIF, the National Ignition Facility, is currently the reference inertial confinement fusion facility, but it's not the only one. We can talk also about laser megajoule, located in France, and which is the largest ICF experiment outside the United States. LMJ has 22 laser beam lines. Each of them delivers 1.8 megajoules of total energy to the target, and it does it in indirect lining, just a little lower than NIF. Which is the most significant difference between LMJ and NIF? Well, in contrast to NIF, which uses individual amplifiers for each of its 192 beams, LMJ system is arranged so that beams are sent into amplifiers in groups of 8, arranged as 2 groups of 4 beams, and one quad above the other. So this is really a really big advance in terms of laser efficiency. We are not needing 200 lasers, but just about 20 lasers to get almost the same energy. So it's a really big advance in laser efficiency. And well, finally, as you just saw for magnetic confinement, we have to work with this NIF and LMJ facilities until we fully had understood plasma and develop the materials and associated technologies we will need to operate an energy profitable reactor. And then we will have to prove that this kind of reactors are economically profitable too. So we will need to build demonstration IC power plants. And one of these project, Generation 1 ICF reactors or inertial confinement demonstrators, is LIFE. Life, as you can see in the screen, is an evolved version of NIF that aims to lower costs. Actually, it is planned to use a national ignition facility and adapt it to become live. But I have to say that this project is now frozen because although I said that NIF reached the break-even in 2013, well, this experiment has not achieved its ignition-related goals yet. So it's not a total success, and it has impacted in life schedule. The other project which is under consideration is Hyper, which is the European proposal. And in this case, you can see we are still really far from phase 4B, but it's remarkable that Hyper is planned to be designed to study the fast ignition approach, which uses much smaller lasers than conventional ICF facilities or designs, but yet produces fusion power outputs about the same magnitude. So it's a really interesting approach to ICF. And I hope I fit to time, so just 3 sentences to resume this lecture. Technological challenges are greater than those related to plasma physics. In example, we have not even mentioned plans for a realistic factory because it is still out of the roadmap. So, well, the development of the ICF is marked by the work on NIF. Scientific break-even was reached in 2013, but the ignition results were not expected, and this has badly or negatively impacted in plans for other IC laboratories. And finally, well, demonstration facilities are planned to be built, but they will not be commercial reactors yet. Thank you very much for your attention, and all your questions will be welcome at the end of the session.